Hello friends, good afternoon and welcome to our next session on structural analysis. Today we have a different problem and there is some difficulty level that you have to understand. So let us start with the analysis of this particular two-span continuous beam where we can see a new type of support, spring support. Okay, so as you can see, AB and BC both spans are of 3 meter each, and there is one more thing, there is no intermediate loading on spans AB as well as BC. There is only one 50 kN point load vertically downward which is on joint C. Joint C is supported by spring support, its stiffness has been given, and there is one more thing that is given. E is 200 gigapascal and I value is 2 into 10 raised to minus 4 meter raised to 4. Okay, so this is what has been given and we have to start with the analysis. So first of all, unknown displacement quantities will be our first step, that will be kinematic indeterminacy. So what is kinematic indeterminacy of this beam? It is 3. There are 2 rotations as usual, but there is additional unknown displacement quantity delta C. Because it is a spring support, because of 50 kN load, spring is going to get compressed vertically downward, so that will be linear displacement of the support C or joint C in vertically downward direction. So that is additional degree of freedom, delta C. This delta we have also seen in sway type of portal frames by stiffness matrix method. Its number, we used to bring this unknown on first place. That is what we have seen. Here we have kept it on number 3. Okay, so numbering to these unknowns is important again. So delta 1 we shall say theta B, delta 2 theta C, and delta 3 is delta C. Okay, so these are our unknowns. Second step, now in all types of problems or all problems previously for stiffness matrix method, we used to have first we used to find fixed end moments, and then we used to get summation of fixed end moments on different locations. Here all fixed end moments will be 0. Why? Because there is no intermediate loading. MFAB, MFBA, MFBC, MFCB will be 0. So there is no question of finding out fixed end moments. Hence there is no question of finding out summation of fixed end moments on joints B and C. So PL values will be 0. P1, P2 values will also be 0 because there is no external couple on 1 and 2 locations. However, there is 50 kN vertical load. So P3 will be minus 50. That we will note down. So PL values are 0. PL1, PL2, PL3 all are 0. P1, P2 are 0. Okay. P3 is minus 50. Why minus? Because it is vertically downward. Okay. So now second step will be, now we have to jump to our step number 4 directly. What is step number 4? Take our unknowns one by one, make them one value, make other unknowns 0 and find out stiffness matrix elements. So apply unit rotation at 1. This will be our next step. Apply unit rotation at 1. Okay. So corresponding to this we will find 3 stiffness values one by one. So first of all, draw the deformed shape of the beam because of unit rotation of 1. Okay, this is 0. So B joint is here, we are going to rotate it. So what will happen? This will be the deformed shape. Okay, this is 1 radian rotation, and here is value 4EI by L1, here 4EI by L2. Its half value will be carried over to joint C. So this is location 1. 2 and 3 are on joint C. Locations 2 and 3 are on joint C. So we will find out what are stiffness values because of unit rotation of 1 by 1 on all 3 locations. So K11. So what is on 1? Moment at 1 due to unit rotation of 1. Okay, so what is value? These two, 4EI by L1 plus 4EI by L2. First value is from span AB, second is from span BC. So 4EI by 3 plus again 4EI by 3. Both spans are 3 meters. So it is 8EI by 3. K11. We will keep it as it is just for the ease of calculation, nothing else. Okay. Then go to location 2. There is one value of stiffness K21. What is K21? Moment at 2 due to unit rotation of 1. Okay, so what is the value? 2EI by L2 for span BC. So how much is this? 2EI by 3. Then K31. Now K31 will be a reaction, not a moment like these two. Why? Because our third unknown is delta C. So what we will do? We will take free body diagram of span BC. Here we shall show what are the stiffness values from this diagram. So 4EI by L2 here, and here is 2EI by L2. Now we want reaction on joint C. So I shall assume direction of this reaction upward. So this is K31. Okay. This direction I will assume downward. I have assumed these directions because these two reactions will produce an anti-clockwise couple. Because 4EI by L2, 2EI by L2 both are clockwise. So clockwise moment should be equal to anti-clockwise moment. Simple. So this is L2 or 3 meter. So we will take summation of moment about joint B. So minus K31 into L2 plus 4EI by L2, okay, plus 2EI by L2, it is equal to 0. So K31 is 6EI upon L2 square. So this is for span BC. Okay, so 6EI by 3 square. 6EI upon 3 square. L2 is 3 meter. L2 is 3 meter. So 6EI by 3 square is 6 by 9. It means 2 by 3. So value is 2EI upon 3. K31 is 2EI upon 3. Next, step number 3. Go to second unknown, make it 1. So apply unit rotation number 2. Okay. So again, draw deformed shape. And apply unit rotation here. So this is location to here. Deformed shape will be something like this. Okay. So this is 2 here. Value will be 4 EI upon L2. Here value will be 2 EI by L2. Okay. And third value we will again find using this procedure. So this is location 1, 3 is also on joint C. Now we will just note down these values here. K11 is 8 EI by 3. Okay, 8 EI by 3. The remaining 2 are here. 1, 2 and 3. So we will just note down here. Second value is 2 EI by 3. Third is 2 EI by 3 again. Okay. Just for reference we are writing them down because we will need them at a later stage. Now we will continue from here. So look at location 1. What is value? 2 EI by L2 because of rotation of 2. So K12. We will get K12. What is K12? Moment at 1 due to unit rotation of 2. So how much is value? 2 EI by L2 for span BC. It is 2 EI by 3 over. Then K22. What is K22? Moment at 2 due to unit rotation of 2. How much is the value? 4 EI by L2. Again it is from span BC. Okay. How much is the value? 4 EI upon 3. Correct? 4 EI by 3. Now we want K32. What will be K32? Reaction at 3 because of unit rotation of 2. So again take this free body diagram. Show the stiffness values. Here is 2 EI by L2. This is 4 EI by L2. And this is reaction. So again we will show reactions in such a fashion that they are causing anti-clockwise movement because the beam is subjected to these two clockwise movements. That's it. So K32. Am I correct? 1, 2, 2, 2, 3, 2. Yes, K32. Again this is L2. So summation of movement about B is equal to 0. So minus K32 into L2 plus 2 EI by L2 plus 4 EI by L2. So I'll write directly 6 EI upon L2. It is equal to 0. So K32 is 6 EI upon L2 square. So how much is the value? 6 EI upon 9. It means 2 EI upon 3. K32 is 2 EI upon 3. Okay. So we will note down them here. So K12, so this will be here 2EI by 3, 2EI by 3. K22 will be 4EI by 3. This is K32, 2EI by 3. Two more are remaining. Now we will take third unknown, make its value 1, and we will again find 3 stiffness matrix elements. So step number 4 now. What will be step number 4? Apply unit vertical displacement at 3. Apply unit vertical displacement at 3. So we will apply vertically upward. We can apply it in any of the options, either upward or downward. So I am applying it upward. Okay. So if you allow this joint to go up by unit value, it will be nothing but upward sinking of the support or upward swing. Okay. So what will be value here? Fixed end moment because of sway is 6 EI, delta is 1 upon L2 square. Same will be here, 6 EI upon L2 square. Okay. Now we will find what are its stiffness values because of this unit vertical displacement. So two of the values are ready with us. So this is 1, this is location 2. So on 1 and 2 we have the values. What are they? 1, 3, K13. Moment at 1 due to unit vertical displacement of 3. Okay, what is the value? 6 EI upon L2 square. This value is positive because movement is clockwise. So this is for span BC. So again 6 EI upon 9. It is 2 EI by 3. K13. First row, third column. Okay. K13. Then K23 is moment at 2 due to unit vertical displacement of 3. What is the value? Again same, 6 EI upon L2 square. Again it is for span BC. So 6 EI by 9, it means 2 EI by 3. 2, 3. Second row, third column, it means here 2 EI by 3. And it is equal to K32. Third row, second column. So these two are equal, these two are equal, these two are equal. Now remaining is only K33. So how to get? We need reaction. So again take free body diagram of beam BC. So there are the reactions. What are the reactions? 6 EI upon L2 square, both values. Okay. 6EI upon L2 square. So here the reactions will be this downward, this upward. How have I selected? Again, net moment this beam is subjected to is a clockwise movement, so reactions should be creating anti-clockwise movement. So this is L2 span. These two moments are 6EI upon L2 square each because of sinking, upward sinking. So K33 summation of moment about joint BU tech. So minus K33 into L2 plus 2 times 6EI upon L2 square. So it will be 12EI upon L2 square. It is equal to 0. So what is K33? 12EI upon L2 cube. So this is again for span BC. So what is the value? 12EI upon 3 cube is 27. It means 4EI upon 9. Okay, 4EI upon 9. Now here is the change. What is the change? On location 3 there is additional stiffness of the spring also, and that we have to take into account here. Okay, so 4EI by 9 plus 200. 4EI by 9 plus 200. That is only the change that we have to consider, and then we can now solve the 3x3 inverse matrix and find the unknowns. Okay. So now step number 5 is our matrix equation. Okay. So what is matrix equation? First of all, these unknowns on left hand side, delta 1, delta 2, delta 3. It is equal to K11, K12, K13, then K21, K22, K23, then K31, K32 and K33. So inverse of this 3x3 matrix multiplied by P1, P2, P3 minus PL1, PL2 and PL3. So out of these 6 values, pi are 0, P3 is minus 50. That we shall substitute. So first of all, K values, they are here, 8EI upon 3. Okay. Then 2EI upon 3. Again 2EI upon 3. Then here also 2EI upon 3. Here also 2EI upon 3. Then 4EI upon 3. 2EI upon 3. 2EI upon 3. Then 4EI upon 9 plus 200. So inverse of this matrix into 0, 0, minus 50, minus 0, 0, 0. Now we have to solve this inverse of the matrix. So we will first of all make some minor adjustments. Everywhere we can see EI upon 3 common in all these matrix elements. So we will take it outside as a common entity. So EI upon 3 inverse is 3 upon EI. So let us write down first of all this. So this is delta 1, delta 2, delta 3. It is equal to 3 upon EI. Okay, this is common. What is there now inside the inverse of the matrix? 8, 2, 2, then 2, 4, 2, then 2, 2. Carefully see here now. We are taken EI upon 3 common from this. So if you take EI upon 3 from this term, it will remain 4 upon 3. Okay, from this first term only, 4 upon 3. So what is 4 upon 3? 1.33. 1.33 plus 200 is 201.33. So 201.33. The third element, inverse of this matrix, multiplied by 0 minus 0 is 0. Then again 0 minus 0 is 0. Minus 50 minus 0 is minus 50. Yeah. Now we will take inverse of this matrix. As you can see, I have got the inverse of 3 by 3 matrix. I have used this by method of cofactors. I won't go into the details of the same. Second important thing, we have been given E and I values. Now we need to bring these values here. So first of all, convert these values into appropriate units. E value here, we need EI term. So I have got this here. E value has been given as 210 gigapascal. It means 210 into 10 raised to 9 Newton per meter square. Okay. So convert this in kilonewton per meter square. So divide this by 10 cube. So it will become kilonewton per meter square. Multiplied by I value, keep it as it is because its unit is in meter. Okay, meter raised to 4. So EI value comes to be 420 into 10 raised to 2 kilonewton meter square. Our loads are in kilonewton, distances are in meters. Hence, unit of EI should be in kilonewton meter square. Simple. So EI value I have substituted here. This bracket is the determinant of 3 by 3 matrix. Okay. So 801.32, this is cofactor, multiplied by 8. Then minus 398.66 into 2 minus 4 into 2. Okay. The rest of the cofactors are here into 0, 0, minus 50 as it is. Now first of all we will simplify this ratio and see how much is the value. Okay. So in the denominator 420 into 10 square into bracket 801.32 into 8 minus 398.66 into 2 minus 4 into 2 is 8. So the denominator is 2.35 into 10 raised to 8. Okay. So 3 divided by 2.35 into 10 raised to 8. So this value is 1.27 into 10 raised to minus 8. This total ratio is 1.28 into 10 raised to minus 8 multiplied by this bracket or this matrix as it is. Okay. So I'll just write here delta 1, delta 2, delta 3. It is equal to 1.28 into 10 raised to minus 8 multiplied by multiplication of this matrix. Okay. Now we will find one by one the values of deltas or the unknowns. So delta 1, what is delta 1? 1.28 into 10 raised to minus 8 multiplied by 801.32 into 0, forget about it, minus 398.66 into 0, again skip this, multiplied by minus 4 into minus 50, so it is 200 plus 200, so plus 200 into this value. Okay, so 200 into 1.28 into 10 raised to minus 8. So answer is 2.56 into 10 raised to minus 6. 2.56 into 10 raised to minus 6. Then delta 2. Again 1.28 into 10 raised to minus 8 multiplied by minus 398.66 into 0. Skip. 1606.64 into 0. Again skip. Minus 12 into minus 50. Minus 12 into minus 50. Okay. So 12 into 50 into 1.28 into 10 raised to minus 8. How much? 7.68 into 10 raised to minus 6. 7.68 into 10 raised to minus 6. So these are theta B and theta C. Now delta C, which is delta 3, 1.28 into 10 raised to minus 8 multiplied by, now come to third row, minus 4 into 0, need not be considered, minus 12 into 0, again 0. So remaining is 28 into minus 50. Okay, 28 into minus 50. So this one answer will be minus. So minus 28 into 50 into 1.28 into 10 raised to minus 8. So answer is minus 1.792 multiplied by 10 raised to minus 5. Okay. Now we will make use of these three values to find final moments. So step number 6, final moments. So these are final moments, and we have made use of slope deflection equations, and we have substituted these unknowns that we have found in slope deflection equations, and we have got these values. Now we will draw BMD. Now here we need not draw SFD first because there is no intermediate loading on beam. So there is no point of zero shear force, okay, anywhere. So we can directly draw BMD. So let us draw it. Positive values will be plotted above the reference line, negative values will be plotted below the reference line. So MAB is plus 0.07168, okay, kilonewton meter. Then 0.14 minus 0.14336 kilonewton meter, and then 0. So just these 3 points are there that are to be joined. So let us join them. So this is plus, this is minus, over. Our bending moment diagram is over. So this completes our problem. So friends, if you have any difficulty in understanding this question, continuous beam with spring support, please do write in the comment.